Hello everyone, welcome to Homework Help. If you find the videos useful, please subscribe to the channel. So in this video, we'll solve this problem using the concepts of second derivative. So as per the problem, each graph represents the second derivative double prime of f at x, on which intervals is the graph of f at x concave up and down, list all points of inflection, make a rough sketch of f at x assuming f at 0 equals 2. So let's start with the first given graph. This graph is a straight line that's sloping down from left to right, and this is the graph of second derivative of f at x. So first we have to find the intervals over which the graph of f at x concave up and down. Now we know that if the second derivative of a function is greater than 0 for x values, that means the graph is concave up on that interval or for those x values. So I'll write it on the board. So if the second derivative of f at x is greater than 0, that means the graph is concave up for those x values or in that interval. And if the second derivative of f at x is less than 0 in an interval, that means the graph is concave down in that interval. So in order to find the interval over which the f at x is concave up for this first function, we need to find the x values for which the graph of the second derivative is above the x-axis. Because when the graph is above the x-axis, that means the value of the second derivative is greater than 0. And that's for x values to the right side of 1. So that means the interval for concave up is x is less than 1. Now in interval notation, we can write this interval as negative infinity to 1. Now we can write the interval for concave down. So that's the interval over which the graph of the second derivative is below the x-axis, and that's to the right side of x equals 1. So the interval is x is greater than 1, and in interval notation we can write it as 1 to positive infinity. So we are done with the first part. Now we have to list all points of inflection. So points of inflections are points where the second derivative is either equal to 0 or undefined. So in this graph, there is one point where the second derivative is equal to 0, and that's the x-intercept of the graph, and that's at x equals 1. So the inflection point can be written as x equals 1, or as an ordered pair, we can write it as 1, 0. So that means the f at x has just one inflection point. Now we can do the third part where we have to make a rough sketch of f at x assuming f at 0 equals 2. So here we are given one point that lies on the graph of f at x, and that point is 0, 2. So that's the y-intercept. So now we can graph f at x. So let's assume the given point is somewhere here, that's 2. So this point lies on the function f at x. Now we can analyze the intervals for concave up and concave down to sketch function f at x. Now the graph is concave up to the left side of x equals 1. So let's assume x equals 1 is here. So that means we can show the graph on the left side as like this. So I can just make it a bit better. So we can show it like this. And then it continues like this. Now, to the right side of x equals 1, the graph concaves down. So we can show that at x equals 1, the graph turns down because we have to show that it's concave down. So this can be the sketch of function f at x for the first given graph. So now we are done with the first part. So I'll just make it a bit smoother. So yeah, this is better. So now we are done with the first given graph. Now let's analyze the second graph. So we have to use the same concepts. So interval over which the second derivative is greater than 0, that means the function f at x is concave up in that interval, and where the second derivative is less than 0, in that interval, the f at x is concave down. So we have to find the intervals over which this graph is above the x-axis. So in this case, the graph is above the x-axis over two intervals. One is to the left side of 0 and to the right side of 2. So that means there are two intervals over which f at x concaves up. So the first interval is x is less than 0 or x is greater than 2. Now in interval notation, we can write it as negative infinity to 0 and then union 2 to positive infinity. Now we can write the interval for concave down. So that's the interval over which the graph of the second derivative is below the x-axis, and that's between 0 and 2. And in interval notation, we can write it as, so now we can answer the second part where we have to write all the points of inflection. So points of inflection are points where the second derivative is equal to 0 or undefined. In this case, the graph of second derivative crosses the x-axis at 2 points, x equals 0 and x equals 2. So that means there are 2 points of inflection. And the points of inflection can be written as x equals 0 and then x equals 2, or you can also write them as ordered pairs as 0 0 and 2 0. So these are the 2 points of inflection for f at x. Now we can make a rough sketch for f at x for the second given graph. So we are given the point 2 0 lies on this function f at x. So let's assume this is the point. Now we can analyze the intervals for concave up and down. Now, as per our analysis, the graph concaves up to the left side of 0. So we can show the graph on the left side like this. And the graph concaves down all the way to 2. So let's assume 2 is somewhere here. So from here, so now the graph will start. It's going down to show it's concave down, and then at x equals 2 to the right side the graph is concave up. So we can show that like this, down, and then it starts concave up like this. So we can see that the graph changes its concavity at x equals 2. So this should be the sketch of function f at x for the second graph of double prime of f at x. So these are the steps you have to keep in mind to solve a problem like this one. So I hope you'll find this video useful. Please share it, like it, and subscribe to Homework Help. Thank you very much and have a nice day. Bye.